Well, welcome on this beautiful Friday evening in San Francisco. Welcome to the Exploratorium Observatory and everybody out there on Facebook Live watching this stream. We're coming to you from the Bay Observatory, which is actually the perfect place for us to be celebrating Ocean Discovery Month, not just because you can see the ocean from here, but a lot of exhibits that we have here and the views that we have here really are about the San Francisco Bay Area, which is really kind of dominated by the bay and the ocean. So one of the things that we're doing during this month is celebrating our partnerships with researchers who study the ocean, research the ocean and study about how to protect the ocean. And NOAA has been one of our primary partnerships in the ocean since 2008. Just this morning, we installed a autonomous ocean robot called a sail drone, and it's out on our outdoor area, which you can check out after the talk. And other events are listed on our calendar, on the Exploratorium website calendar under Ocean Discovery Month. So we'll be going all the way through Labor Day with some really fun and exciting programs and events. So I was asked recently, why devote a whole month to studying the ocean? And it was kind of an easy question for me because I just love the ocean. I love the animals in the ocean and coral reefs, but really the oceans are the life support system for the planet. They provide half the oxygen that we breathe, but they're also really the basis for a lot of the systems, Earth systems, including climate and weather, which we're going to be talking about tonight. And the person who's going to be really leading us in that discussion is Brian Garcia, who is the warning coordination meteorologist at the National Weather Service, the San Francisco Bay Area, which is actually in Monterey, not San Francisco. So he had a little bit of a drive today. And Brian is really the perfect person to talk about why the ocean is critical to understanding weather, not just because he has a deep passion for the ocean. He actually named one of his sons Ocean, I understand today, which I think is real commitment. Brian is a lifelong surfer, and he knew from early experience that weather out in the Pacific is really what drives ocean waves. The best waves are really predicted by storms. Brian is a West Coast guy. He was born at Stanford and grew up in Seattle. He attended the University of Washington, which has an excellent atmospheric science department. He worked as a meteorologist in Houston before moving over to NOAA in the Ocean Prediction Center in DC. I suspect Brian missed the West Coast because he moved to the Eureka office of the National Weather Service before coming to the local office down in Monterey, where he's been for the last 2.5 years. So Brian is here to answer the rest of the question, why do you need to know about the ocean to predict the weather? Thank you so much, Brian, for being here.
Yeah, thanks, Mary. All right, good evening, everybody. Thanks for coming out, and everybody on Facebook Live, thanks for streaming in, I guess. It's not dialing in anymore, I guess it's streaming in, right? So, again, like Mary said, my name is Brian Garcia. I'm the warning coordination meteorologist for the National Weather Service out of the Monterey office, which services the San Francisco Bay Area. So we have a huge swath of land that we cover. Like Mary said, I did get into weather because of the ocean. I have a problem. I'm actually seeking counseling for this right now. It's called surfing. So I like to be in the water as much as I can, and it's actually what got me into weather in the first place. A lot of people get into weather because of severe storms, because of a tornado that ripped through a house next door, but their house didn't get knocked down. Me, it was just because I wanted to know where and when to go surf, is kind of what it boiled down to. So yeah, it's a problem. So I'm going to be talking about weather in the Bay Area, but we're also going to be talking a little bit about observations and some other things. So if anybody in the audience has questions along the way, I'm a very informal presenter, so feel free to ask, feel free to shout them out. I'll repeat the question so we can get them on Facebook Live, and I'll try to answer them as we go along, but we'll also have some time afterwards. So this is a picture I took at the Marin Headlands last year, I think it was. I thought it was really fun because what more San Francisco can you get, right? It's like the clouds rolling in over the peninsula, everything's kind of socked in. I actually had some other pictures I probably should have put in. But like a half hour later, of course, it cleared out and it was beautiful. So we'll be talking a little bit about why this happens, what role does the ocean play in this. And Mary kind of alluded to, this Ocean Discovery Month. What does the ocean have to do with weather and climate and all that sort of stuff? It has everything to do with weather and climate. Whether you're in the Midwest, the Canadian plains, like up in northern Saskatchewan or something like that, wherever you're at in the world, the ocean is the reason you're having the weather that you're having, which blows my mind. I love it. Okay, so I guess where I'm going to start here is, why does weather happen? That's kind of just kind of a weather 101 question a lot of people ask. What makes weather? Well, for that, you kind of have to take a step back from our Earth, and you actually have to go into space, and we have to start talking a little bit about astronomy. So for weather, all the world wants to do is be in temperature equilibrium. That's all it wants to do. It just wants to have everything be happy and copacetic. But because the world is tilted on about a 23.5 degree axis, and it rotates around the sun on that axis, we get what we call differential heating. So in other words, different parts of the Earth get heated differently. So in the winter months, for example, in the northern hemisphere, it's really cold up at the North Poles, right? And the equator's somewhat warm. Whereas the South Pole is a little bit warmer during their summer, our winter, and so it's a little bit warmer down there. So up here, our temperature difference between the polar region and the equatorial region is quite significant. And because of that, the Earth kind of throws some curveballs into the extratropical latitudes. So in that 30, 40 degree north range, so Oregon, Washington type range. And it's trying to mix the warm air north and the cold air south. So basic weather 101. With me so far? All right, awesome. So in order to monitor this weather, monitor everything that's happening, we have a lot of different observation systems. And we're just going to go over a couple of these and talk a little bit about why they're important to us in the Bay Area, why they're important to us in the weather world, and in the climate world a bit. And then we'll start to get a little bit more focused down into our area. So we started in space. Now we're coming down towards the Earth's surface, and then we'll get down into our local area. It's what we in the weather business call the forecast funnel. We go from the top down. Okay, so profiler, radar, wind. So we're going to talk about profilers, which is kind of cool because we actually have a couple of them here in the Bay Area. The image on the right is from our Bodega Bay profiler that the Naval Postgraduate School has out. So they're located down in Monterey. And it's actually really kind of cool because we get to look at that image over there on the right, and you can kind of see the blue colors down low up to about 500 meters or so, and the legends up top. Those blue colors are about 14 to 16 degrees C, somewhere in there. And then you get above that, and the temperatures go up to like 20, 24 degrees C. This is kind of counterintuitive. This isn't necessarily what we think should be happening, but this is summer on the West Coast. This is what we call our inversion, or our marine layer. So all of that blue, that's kind of that cold, moist air right near the surface. Get up above that, and we're starting to talk a little bit about warmer temperatures up top. And then you can also see the wind barbs on there. And I'm just going to walk over here and point out the wind barbs really quick. The wind barbs are coming from the northwest here. So it's not pointing to, they're coming from. So the wind's coming out of the northwest. So that's our typical wind pattern in this area. So we get winds out of the northwest. So if we look at this animation on the left, we can actually see some of the observation sites across the area, all the green dots, and you can pretty much see the wind coming in from the ocean, pushing into the land. And then there are some spires, towers in this. One's down by Monterey, down by Point Sur, and then the other one's up at Bodega Bay there. Those are the profilers showing you the wind at various heights. So we look at this a lot to get an idea of what's going on in the atmosphere locally and to get an idea of the depth of the marine layer in our local area. Okay, so those are coastal profilers, which are very cool, but we also do balloon launches because we want, like we saw here, we want a vertical profile of the atmosphere. We want to know what's going on from the ground up. So we have several offices around the nation in the National Weather Service, like this picture shows here on the left, that launch weather balloons. This image is actually from the New York office, so they're out on Long Island. Stole this off the internet. They had a school group out there showing how they do balloon launches. So this diagram right in the middle here, this is what we call a skew T. So it shows us what the temperature and moisture profile is in the atmosphere going from the surface all the way up. And this just so happens to be, if you see at the top left there, it's from Oakland International Airport, so right across the bay here. And these get launched twice a day, so at 0Z and at 12Z. And if you ever wonder what your time difference is for Z, we're about 7 hours off. We're 7 hours off here during daylight time and 8 hours off during standard time on the West Coast. So these are very important measurements for the atmosphere because, like I said, it gives us that vertical profile through the atmosphere. And if you look down at the very bottom where those black lines start, it's, by the way, the temperatures are down there in the blue at the bottom, so 0, 10, 20, 30, 40 degrees C. And you can see down low, it's around 15 degrees C, somewhere in there. But then you go up a little bit, and the temperature, the right black line, warms up quite quickly. And if I go back to, look at that, it warmed up quite quickly in the yellow. So it matches the observations quite well. So these are very important. These all go into numerical models that help us get a look at the atmosphere. But also important, and one of my favorite things, are buoys. I love buoys because they tell me when and where to go surf, which is fantastic. So buoys, we have buoys everywhere. We have relationships with other countries around the world, so countries in Europe, Japan, Asian countries, South Pacific, South Atlantic. Anybody who has buoys, we like to share all of our data. And it all gets housed on the National Data Buoy Center page. And you can see all of the dots on this page are buoys. Some of them aren't working right now because maintenance can kind of be an issue. I mean, think about it. Going out into the middle of the ocean and trying to maintain a buoy, you don't always get to go out into the middle of the ocean. It's not like just going down the street and maintaining a weather station. You actually have to take a ship out there and maintain it. But they get out there as best they can. I'll show you on the next slide. But this buoy on the upper right there that says NOAA on it, that one is just out at Half Moon Bay. So it's just outside Half Moon Bay. It bounces around out there. I pulled an observation off of it, so you can see it says significant wave height, for example, and you go over to the right. It was 4.3 feet when I pulled this off yesterday. And then down low, some of the buoys now have cameras on them, so we can actually see what's going on out in the ocean, which is very cool for us because, I don't know how many of you guys remember Car Talk. There used to be a show on NPR called Car Talk with Click and Clack, the Tapper Brothers, right? And at the end, they would have these fake names about people who sponsored their show or helped. And one of them was their staff meteorologist, and the guy's name was Look Out the Window. So this gives us the look out the window, which is very nice. And the era of webcams has been very good for that because we can't be everywhere all the time around the region, so we have to be able to utilize things like this. And in all honesty, that's not the reason they put cameras on these buoys. The reason they put the cameras on the buoys was for vandalism. Because people will go out there, if it's their favorite fishing spot or something like that, they'll actually cut the buoy loose and let it go, or they'll accidentally run over the buoy or something like that. So we like to be able to see what's going on and maybe hopefully get a ship marking or something like that so that we can actually find the people who did it. So down in the tropical Pacific here, so between South America and Southeast Asia, we have a whole array of buoys. These are called the TAO buoys, and now I'm going to completely space on what TAO stands for, Tropical Atmosphere Ocean, if I remember right. But there's a whole array of buoys down there that measure the sea surface temperature all the way down deep into the ocean, hundreds of meters deep, as well as atmospheric data right at the surface of the water, which is great because this is the area that the ocean is so ridiculously important for because we get the data as to whether or not it's going to be El Nino, La Nina, which is a huge driver of global weather patterns. So when I talk about the ocean being an integral part of the weather around the world, this is one of the huge drivers. And in case you guys didn't know how they named El Nino, it was the South Americans. They're on the beach, they're fishing there all the time, and they're out in the waters, and every once in a while, around Christmas time, they would notice the water's getting really, really hot, or warmer, anomalously warm, and they were like, this is really interesting, and they likened it, or they tied it to the time of year, so it was Christmas time, so it was El Nino, the Christ child. So, and then, of course, the converse, the waters got cold, so the scientific community took El Nino, and we decided to call it La Nina. And then, of course, there's the in-between, which technically it's called neutral, but I don't like neutral, so, of course, I have to call it La Nada. So this is one of our NOAA ships out servicing the tau array, and if you can see on the top of the buoy, somebody's actually up there servicing that site, which is, what a cool job. I get seasick personally, but that would be a cool job. So they're out there a lot on the ship servicing things. So going from the ocean, going back up into space a little bit, let's talk a little bit about satellites. There are a lot of satellites out there now. Just, what was it, 40, 50, 60 years ago, there was like one. And like one weather satellite, and the U.S. government put it up, and it brought back pictures, and it blew everybody's mind, and so we've just continually been putting satellites up there for all sorts of purposes, whether it be GPS satellites like in the upper right, satellite radio now we have satellites up there for, right? So private satellites, government satellites, all sorts of stuff. We have polar orbiting satellites, geostationary satellites. By like every country you could possibly imagine, anybody who's got some money to spend on putting a satellite up in orbit, they pretty much have, which is really cool, especially if they like to share the data, because that means we get more data, which is, for nerds, it's like the best thing ever. So the circle around, all the way around the globe, like on the left here, you see GOES E, which stands for goes east, and then we have GOES W, goes west. Those are our satellites. We actually have some more up there as well now. But those are all geostationary satellites. So when we talk about geostationary, we're talking about they're hovering at the equator at a certain longitude, and they're looking at a hemispheric scale look of the Earth, which is really cool. But then you have all these other ones looping up around over the Earth and stuff like that. Those are in a much tighter orbit around the Earth, and they actually get like flung around by the gravitational force and stuff. It's really cool physics. But those rip around the Earth, and we get pictures of the polar regions with those as well, because the ones at the equator, once you start looking up towards the polar regions, you can't really like make it out. It gets all kind of funky and like skewed and weird, and I'll show you kind of what that looks like here in just a moment. As a matter of fact, so this is a satellite image I pulled off the College of DuPage webpage. This is from GOES 16, which is our, second newest satellite, because GOES 17 is up there right now, but it's having issues. So GOES 16 has become GOES East. So it sits out over kind of the East Coast region, looking at that hemispheric scale. But we can still see a lot. But if you look out on the left side here, way out at the edge, you can kind of see how it gets blurry out at the edge. That's because it's going around the curvature of the Earth. I'm sorry, flat earthers. Don't mean to offend. I'm just here to talk about science. So the Earth does curve, and so the satellite's trying to read around it, but obviously can't go all the way around the curvature of the Earth. So this is these satellites that have recently gone up, GOES 16 and GOES 17, they were a quantum leap forward for us in observations of the Earth system. Why, you might ask? Well, because they have more instruments on them than we've ever had before. But for us in operational meteorology, doing the day-to-day forecasting type stuff, watching for hurricanes, tornadoes, wildfire smoke, all that sort of stuff, these now give us imagery every 5 minutes, whereas before we were getting like every 15 minutes. So what we call temporal resolution, so we're starting to tighten that time. The temporal resolution has gotten tighter and tighter. And then we also have two sectors that we can move around. We can task the satellite, say, hey, look over here. And the satellite will look over there. And we can get those in 1 minute segments, so little 1 minute pictures. I think, and I should have probably put this in the slide deck, but I think the coolest thing that we did with the Ghost 16 was Hurricane Harvey. I don't know if you guys remember Hurricane Harvey. It went into the Houston area and dumped something like 45 inches of rain or something like that in Houston, right? What they did with Harvey is they took the two areas that we can task the satellite and they put them both on top of Harvey. And so we weren't getting 1 minute data, we were getting 30-second data out of the satellite, which was amazing because now we could see the evolution of a tropical system in almost real time, which was incredible. So Google it. I'm sorry, I can't support any specific search engine. Use your favorite search engine and look for, just search the Hurricane Harvey satellite image or something like that. It's phenomenal. It's beautiful. It's frightening too. But it is definitely worth a look. So one of the things I want to point out on this, and it's going to loop back around here in a second, I want you to look up in the Pacific Northwest and up into Canada, because you're going to see kind of a dark haziness up there, and you can actually see it all the way out towards Quebec and northeast Canada as well. That is all smoke. We think California's burning right now, by the way, or the West is burning because we're kind of, US-centric, which is fine, don't get me wrong. But Canada is legit on fire. They have a lot of land to burn up there, and they're burning it well. Look at that. Pretty much you got 3-4 provinces almost completely covered in smoke up in Canada. Whereas down here, we've got the West covered in smoke, but nothing like the square mileage of Canada. So this is another benefit of the satellite. We can see where the smoke's drifting, and there's actually almost a weird, let's see if I can, nope, back. Right around here, there's actually kind of almost a smoke front. It's getting caught up in the actual weather patterns, and it's moving down kind of like a cold front, but it's more of a smoke front. It's amazing. So polar orbiting satellites, this is the kind of stuff we get off polar orbiting satellites, and this is the total precipitable water, if I remember right. Yes, from one of the polar orbiting satellites. So it tells us how much, essentially, moisture is in the atmosphere, and as you would guess, the vast majority of the moisture is over the tropics, and of course this is just looking at the oceans. Where the ocean's really warm across the Southeast Pacific, or the Southeast Asia and the Southwest Pacific, you have the very bright colors, so the reds over there, and that's a lot of moisture locked up over the oceans. And all of this is feeding into weather patterns. And oh yeah, no, I gotta walk and talk now because I gotta show you something here. I didn't even. I'm going to do this. You guys are going to kill me. I'm not going to touch the screens, I promise. See that right there? Just watch it. Spinning up. That's a typhoon. So that's the kind of imagery that we get out of these satellites, and we can see the moisture getting wrapped up in this typhoon over by Japan. And ultimately, that typhoon will recurve up into the jet stream and head off towards us, North America. It's pretty cool. So other stuff that we can get from satellites, because it's getting better and better, we get sea surface temperature here on the left, and you see a lot of black. Well, that's because the satellite can't see through the clouds. It's just looking where it can actually see the surface of the ocean. And you see a lot of blues there. The blues are, I don't know, 19, 20 degrees C. But then you get up right along the California coast, and suddenly we see a bunch of purples. Well, what are the purples? The purples are down here in the 15, 16 degrees C range. Why is the California coast so cold? Anybody have an idea? Awesome, because I get to teach you then. And even over on the right, we got the sea surface temperature model. You can see a lot of yellows out there, but then you go along the strip of California there, and we're starting to get into the blues. Very cold along the coast. Okay, so this is one of our atmospheric models we use, and I'm going to hopefully use this in the next couple slides to really illustrate why we get the weather we do around here in the summer. So this is going to be the attempt. If anybody has any questions along the way, please let me know. So typically in the summer, so this image, what we're looking at, just look at the black lines. The black lines are the pretty lines that we want to look at. This is at jet airline height. So when you get on a plane to fly out to the East Coast or something like that, you're flying, like 34,000 feet, something like that. This is about that height. This is what we call the jet stream. Because if you get in this with a plane and you have a tailwind, you're going to get to your destination faster. It's, the pilot comes on, oh yeah, we have a 6-hour, 43-minute flight ahead of us. And then 3 hours and 22 minutes into it, they're like, oh yeah, we have about an hour and 15 minutes left. We got a nice tailwind. We're going to get there early. And it's like, dude, you could have told us that earlier, right? I mean, you're supposed to be getting the weather. I could have texted my mom to be at the airport to pick me up earlier. So this is what you're going for. So typically in the summer, and I'm going to walk and talk, Kale, okay? You ready for me? Okay. So typically in the summer what we get is we get these big areas of high pressure over here. Now high pressure, the winds circulate clockwise. And so we get these big areas of high pressure over here. You can see this little dip over here. Let's ignore that. I'm going to wait till it kind of rolls around again. This is a big area of high pressure right here, that's for sure. And it kind of meets up with this guy over here. There it is, the big bump right there. We get these big bumps over us, and it just kind of sets in place for the summer typically. And then we get these big areas of low pressure out here, but it's really the high pressure we're talking about. So when we talk about high pressure, do you think it's nice and gentle and it's just pleasant to be around? No, it's high pressure. I mean, it's like when you're at your job. It's like, I've got a high pressure job in the stock market. It's like, you're a stressed out job, right? It's like, that's a high pressure job. So's that. It's stressed out. So we typically have high pressure over us. In the summer, this is that same type of chart, the 500 millibar chart. So airplane, jet stream type height. So there's the high pressure up over California. If you can see California here in this black line here. Sorry, I didn't warn you, Kale. How about this? So if we look over on the right chart here, you can see this area right here. This is at the surface. So we've got low pressure at the surface. Well, okay, but you just told me we have high pressure up above us. How does this work? Well, this is just really cool. So let's see if I can make this work. Boop. Boop. Okay. So we have high pressure up above, pushing down. It's compressing everything. When air gets compressed, it likes to heat up. It likes to warm. And then in the summer, I don't know, days typically get a little bit longer, right? You go inland away from the ocean because the ocean out here is typically in the 50s, maybe low 60s. Ocean temperature of the bay is generally in the low 60s, mid 60s. But when we push down on the air, we heat it up. Warm up the surface with the sun as well. And so we're starting to heat everything up. Well, when things heat up, it's kind of like, I don't know, do you guys have an Instapot at home? You guys know what an Instapot is, right? So you heat it up and it pressure cooks the thing, and then you have to release the pressure, right? Well, it's like steam just shoots up out of it, and it's just shooting up out of it. It's the same kind of thing. So we're heating up the surface of the earth, and the surface of the earth is like, hey, dude, I'm tired of being heated up. Let's start moving stuff off of me. And so it starts pumping the air back up. And so the warm air rises. And so we start lifting that pressure back up off the surface. And now we got surface low pressure. So that's what happens kind of on a cyclical basis, on a day-to-day type time frame. Am I okay on time? Okay. Got to check with the boss here. So once we lift that air off the surface, well, there's kind of this thing in science called conservation of mass. We kind of got to shove stuff back in where stuff has been vacated. So now we've got to pull some air from someplace else. Well, the rest of the interior is starting to get warm as well, but the ocean has been maintaining a kind of a constant temperature, constant pressure over it, no big deal. And so it's relatively high pressure relative to that low pressure over the land. So now we have air coming in. So, man, I'm going to skip this and come back to it. So with the air coming in, let's see, where can I go? Nope, I'm going to go back. Okay. So with the air coming in now, we're filling that area in, and now we're also going to be kicking winds in to this equation as well, because we're advecting air into the region. So we're starting to put wind on out over the coastal region here, and that helps to blow the surface of the water along the boundary of the West Coast, which is very cool. So typically in the summer, we have winds out of the north, so coming from the north down south, and during the afternoons, I don't know if you guys have ever experienced this around here, but during the morning it's kind of calm and it's kind of nice and everything's happy and copacetic, and then in the afternoon, you can't wear a hat because it'll blow off your head, right? It's like, that's why, because it gets warm during the day over there in East Bay, and the wind comes rushing in from the coast. So out over the ocean, though, we're blowing the surface water down the coast, and what we get is this little thing called upwelling. So this is one of my favorite things of all time because it blows my mind. So when we have the wind coming from the north going to the south, we're blowing the surface of the water that way. But the earth spins, right? So the earth is spinning under that ocean system. The wind's blowing on it, the earth's spinning under it, and I wonder if you could actually do this. I'm trying to think if I did this in school or not. But if you get a frictionless plane, like an ice sheet or something like that, and get something going, you can actually see this happen. You get what we call the Coriolis effect. So you actually get the surface of the water will be moving that way, but as the earth spins under it, it's getting an effective turn to the right in the northern hemisphere. So we're starting to move the water away from the coast at that point. And so again, we're moving water away from the coast. Conservation of mass. We can't just suddenly have the best tide pooling ever out on the West Coast in the summer, right? No, we've got to replace it with something. So water from the subsurface upwells along the West Coast. So conversely, sidebar, in the winter, we typically get currents coming out of the south because we get storm systems coming in and the fronts roll in and the winds coming out of the south this way, so they're moving water up. And again, curvature of the earth, things deflect to the right. Now we're deflecting it into the coast. And if we get big waves, strong winds, and we get this, what we call Ekman transport, you can see it over there on the right, we could actually get coastal flooding because of all these things happening together, which is just, again, really cool. But because of all this, because of the upwelling, that's why we get that cold splotch along the California coast, and it actually goes all the way up the Oregon coast. I don't know if you guys surf, but if you ever surf the Oregon coast in the summer, it is so cold. It is so cold. It's actually warmer in the winter than it is in the summer to surf on the Oregon coast. And the sharks like it there too. So speaking of sharks, because of this upwelling, we're actually upwelling this very nutrient-rich water coming up from the subsurface. And I'm not a biologist, and I don't claim to be a biologist. I am a meteorologist. I'm a physical scientist, not a biological scientist. I couldn't do biology because I can't remember things well. So I have to have things written down so I can read them. But it's really cool because we get this very nutrient-rich water along the West Coast. And I don't know if you guys realize this, but we have a very vibrant fishing industry in California and in Oregon and even up to Washington, because you have all of this nutrient-rich water coming up, and just outside of the cold area, we have warm water. So we have like fish that like warm water, but they want to get the food from the cold water. They'll go out and punch into the cold water, grab a bunch of food, and then rip back to the warm water and like warm up by the fireplace. And the fishermen know this, and so they go out to these thermal boundaries, and they will literally sit there and just pick off the fish. Tuna's the big one. They'll go out there and just rip tuna up out of it. So it's very cool. So very nutrient rich, and of course, bigger fish eat smaller fish, and bigger fish eat those fish, and so goes the food chain, right? A guy I used to work with up in Humboldt, he used to tell me, enter the water, enter the food chain. So every time I go out surfing, I think of that, and I'm like, okay, I'll take that risk. I should have had this earlier. So this is that circulation that brings the Bay Area fog in. Like I was talking about earlier, the area of low pressure. We have a very special name for this area of low pressure. It's called the thermal trough, because thermal, it heats up, but it creates low pressure trough, so it's thermal trough. A lot of other people call it other things. Here in California, we have special names for everything, of course, right? Because everybody's special. You're all snowflakes. So the low pressure rises, goes back out, high pressure along out over the ocean. In the nighttime, reverse it for most areas, but because our land will stay warm and our ocean will stay cool, it generally holds pretty well for this. Like I said, winds generally come out of the northwest along our coast, which helps to push the fog in, because it's kind of like, think about a hill. You have the H is the high pressure at the surface, so you got a high point, and you got the L, the low point, and so stuff rolls downhill. I won't say what kind of stuff, but stuff rolls downhill. And we end up with, this is actually from last year, we end up with some fog moving into the region, and if you've lived here for any length of time, you know that it generally hangs out right along the coast. In the summer months, if we bring any sort of a little bit of low pressure just kind of sneaking down in, we can deepen that marine layer and shove the fog and low clouds even farther in to the Bay Area. So I'm trying to think. There was something else I want to say about that, but I'm not going to. So there's so much more to talk about. There's so much more to discuss. Like I was telling Mary, who introduced me, I could go on for probably like 3 hours talking about various different things of weather in our area. But at the end of the day, the ocean is the main driver of our weather in this area. It's Ocean Discovery Month here at the Exploratorium. The ocean is an amazing place. And every day that we sit down as meteorologists to look at the weather of our area, we have to take into account the ocean. For example, San Diego recently, just off the coast, actually at one of their piers there, they have a sensor that's been measuring ocean surface temperature for, like 100 years or something like that, more. And they just had a all-time record high ocean temperature there. So it's... Things are interesting. Things are always getting interesting, and it's very fascinating to watch, to see how things are changing. And I'm trying to think if I want to show you one other thing. You know what? I'm going to show you one other thing if you don't mind. Can I show them one other thing, Mary? Okay. Let's see. So I'm going to show you a couple web pages here. This is real-time global sea surface temperature. So this is a composite of, or an analysis of all the observational things that we can possibly get, so you can kind of see where the heat is in the ocean at any given time. And obviously, as you would suspect, the vast majority of the heat is locked up in the equatorial regions, and of course out on the East Coast with the Gulf Stream, because it's essentially bringing equatorial water up north, and then of course cold waters in the polar regions. But this is really the thing that you want to look at if you're ever looking at like the health of our ocean over time and what the ocean is doing over time. You want to look at the anomalies, what the differences are in the ocean compared to what is normal. So these are the anomalies across the ocean. So the departure from normal and the scales down at the bottom with degree C, but you can see that you can see even across the equatorial Pacific, we're warmer than normal, especially up across the North Pacific, very much warmer than normal. Up in the Bering Sea, the Chukchi Sea, a little bit into the Beaufort Sea, and even up in the polar regions. I'm going to click on this. These are the anomalies in the polar regions. So how far are we off of normal? Not so much where the ice is, because, well, the ice is cold. So, but as soon as you get away from the ice edge, look how anomalously warm those areas are. No place has been warming faster on our globe, on our Earth, than the polar regions. And the polar regions are huge drivers of weather because of the ice concentration that they hold, the Antarctic ice sheet, so the South Pole, how that's behaving, how this warm water in the Labrador Strait next to Greenland there, how much warmer that is in terms of melting some of the ice sheet or influencing the weather in that area. So it's a global system. If somebody ever comes to you and says, oh, here's a snowball, you call this global warming, that's your backyard. That's not the globe. It was always cheesy, the bumper stickers, think globally, act locally, but it's so true. It's so true. It's a global system. So just remember, the ocean is a huge driver to everything and anything that we do. Just because you don't live there doesn't mean it doesn't affect you. So with that, I'd be happy to take questions or anything. Mary?